This place, when you look at it, CERN, and you look at the LHC, 27 kilometres of it, seems like a long way to go to answer simple questions. And it is, but it's the only way you can go to answer profound questions. If there was any other way of finding out how the universe works at a very basic level, of finding out truths, essentially, about the way the physical world works, then we'd do it. So what you'd like to do is get a big precision detector, camera if you want, and take it back to the Big Bang and just photograph or look very carefully at what went on there. And you can't do that because it's 15,000 million years in the past. So what you do is you recreate the Big Bang as carefully as you can, with the conditions as close as you can to the Big Bang, very hot, very, very dense energy all crushed together, and just see what happens. Well, we're about 100 metres below the surface of Geneva, and what you can see behind me there is the LHC tunnel. So it's actually been there since the 1980s. There was an old accelerator in there called LEP, and that's been taken out. Nothing there at the moment, but in about a year's time, that'll be full of the magnets and the beam pipes and all the refrigerators that keep it at minus 270 degrees. And the protons are going to thunder down there at about 50,000 times a second. They go around that 27 kilometres, and they'll collide. Some come in this way, some come in from the other direction, and collide right in the middle of Atlas. Protons are tiny objects, but they're going so fast in this detector. I mean, they're going around the ring many, many thousands of times a second. And when they collide together, the energy they have is essentially the energy that things had just after the Big Bang, thousands of a second after the Big Bang. And you've got to contain and measure all that energy. So if you imagine essentially putting a detector around the universe when it was, let's say, 10,000th of a second old, you need quite a big detector to capture everything. If it was small, then everything would just escape and you wouldn't see it. You'd have no chance of picking up what had actually happened.
It looks like really a very expensive signer, but of course you shouldn't forget that this occupies like 5,000 physicists. This experiment alone, the CMS experiment, has like 2,200 physicists which are working on that, so it's not just some hobby of a couple of people. If you have this kind of mass interest in it, it must mean that you're doing something good.
Now that's essentially a big fridge, so the temperature inside there will be something like minus 270 degrees C, and then there'll be an inner ring inside it. So it's just like an annular ring, if you want, with a magnet in there, and that magnet's going to be 4 Tesla. Now what's that? Well, that's 100,000 times stronger than the Earth's magnetic field. So that's actually the biggest high field superconducting magnet ever built. A lot of people see these things and think you go to a company and say, well, go build us a detector. You don't. We've got PhD students, people who got first class honours degrees doing PhDs, and quite a lot of the time they're gluing things together, sticking wires on it and testing if it works. And that's kind of the grubby bit of particle physics that you've got to do in order to do all this wonderful stuff. This is the heart of Atlas, the central bit of Atlas. So right in the middle of this detector is the point at which the protons are going to collide together and explode in that kind of mini Big Bang. You see, it's incredibly complicated objects. I mean, when this is married together with all the other bits of Atlas, there are literally millions of different readout channels or millions of different bits of data. In fact, the number that everyone quotes is 10,000 Encyclopedia Britannicas per second come out of this detector. A lot of the big decisions in particle physics about what to do next, how to find out the things that you don't know, were made in this cafe. And it's one of those things that passes into folklore, but I think it's actually true about this place.
It would be a mistake to think, in all this stuff about the purity of the scientific method, that scientists don't get really annoyed with each other, form cliques, have a lot of politics going on, and occasionally, get pissed together down here as well. And there's a big multinational community of people here. There's a lot of big egos walking around. There's a lot of political issues, and there's financial issues. It all goes on, and underlying it all, there's this physics issue that we want to make the damn thing work. We want to find out, and this is where a lot of those issues get resolved. We
wouldn't spend $10 billion or whatever it is and many thousands of man-years of work building something like this. If there were an easy way to do it, like you just sit there and think your way to the answer. The only way we've got to any sensible answer about the way the world works is to do experiments. It sounds actually quite obvious, but it didn't. The Greeks didn't work that out. It took a long time to realise that the way you find out how something works is to look as closely as you can and as precisely as you can, and just see what you see.